Okay, I've talked more or less about kinematics before. I tried to introduce the notion of the conformal group. It's a finite dimensional group. It's a non-compact group, so that when we start to consider representations which are unitary, they're bound to be infinite dimensional. I introduced the idea of conformal primary fields or conformal primary states. So conformal primaries, they're annihilated by the K generators. And then all states are given by the action of P's and all this. So we can have infinitely many momentum operator or equivalently derivatives acting on the fields, which will generate all possible states. And what I want to consider now are three-point functions. Where we have three fields. And for simplicity, let me consider scalar fields. Now, if they're scalars, and I should put a 3 here, because I'm potentially considering them all to be different. And then for a scalar field, it's characterized by a scale dimension. So it's got a scale dimension delta I, such that when you do a conformal transformation on this, that phi I of x will go to some scale factor omega xi to minus delta I. That's phi I. So that's the behavior. If it had spin, there would be some kind of rotation present as well. Now, because it's the case, there are many ways of seeing this, but when you act with the conformal group on 3 points, it will move 3 points to any other set of 3 points in whatever number of dimensions you're considering, which means that you could just choose this one to be 0, say, this one to be at infinity, and this one just to be some arbitrary point, say the point where one of the coordinates takes the value 1. In which case, there's no dependence on the coordinates, and the thing is just a number. That, if you reverse back from that, it means that we can characterize this in terms of some number, which I'll denote C1, 2, 3, times some function of the x coordinates, which in fact is easy enough to write down because it will be equal to x1, 2 squared times a half delta 1 plus delta 2 minus delta 3. And x1, 2, of course, is going to be the difference between x1 and x2. And then, well, the others we can write down more or less by symmetry. And then one more x3, 1 squared.
What's the fastest way to see that? Is this true in any dimension that I can always move in these two points?
Yeah, I believe that to be true. I mean, another way of looking at it is that if we have 3 points, there are 3D coordinates. If we act with the conformal group, then you would think subtract off because it has this dimension. However, 3 points essentially define a line or a circle, and we have to put back. So this is O d plus 1 comma 1 or d comma 2, and then the number of ways you can rotate a line around is going to be given by O d minus 1, and so this is going to give me d minus 1. And that's equal to 0. So the point is that there are no ways of constructing an invariant so the point is that this is the unique formula. One way to see this is that xij squared under conformal transformation goes to omega xi, omega xj, xi minus xj squared. And then this gives rise to the right behavior according to this result here. So this is the unique expression. Now, let me say a few words, I won't go into any details, about what happens if we have fields with spin. So if we have spin, they have additional labels, let's say I1, I1, and X1. So we have to take account of the spin properties or the rotational properties of these fields when you do conformal transformations. This is an algebraic problem because you can construct, well, there's two ways of producing the right objects. We can either use the inversion tensor, let's say of x1 minus y1, x1 minus x2. The point about this is that this transforms under conformal transformations like a rotation with x1 with respect to this index, or a rotation at x2 with respect to that index. Or we can construct vectors x1 nu. That's right, this is x12 mu over x12 squared minus x13 mu over x13. So this is a vector at the point x1. It's not obvious that that's the case, but nevertheless, if you work through the transformation properties, you can show that this thing behaves like an appropriate vector. So when I say a vector, I mean one which transforms in the appropriate way under conformal transformations. And then it's really an algebraic exercise to see how many different ways you can construct things using these objects. Now, for the case of three scalars, there's only one way. But nevertheless, if we have spins, there are a finite number of possibilities. It's an algebraic problem. It's a bit like coupling spins together when you take the tensor product of two angular momentum states and form another angular momentum state. Well, for ordinary rotations, usually there's just one way of doing this. In this case, there can be a finite number of possibilities. The number of possibilities that you get is independent in general dimension. As an example, let me suppose that we considered the situation of three energy momentum tensors. So this is maybe quite a complicated problem because it's got all these indices floating around, but it's purely algebraic. And it's slightly more complicated because you need to impose conservation conditions, namely that T mu is equal to 0, because that's the property which the energy momentum tensor should satisfy. And then when you go through this algebraic problem, there are three possibilities in general. In general dimensions, except when d is equal to 3, where there are two possibilities. Now, in fact, this corresponds to what you might naively expect or hope, because there are three free conformal field fields. In 4 dimensions, namely those corresponding to massless scalars, massless fermions, and also massless vector fields. In 3 dimensions, we only have 2 free theories that are conformal, namely those involving scalars and fermions. In fact, it's interesting to extend some of these notions to imagining you have higher spin currents. Higher spin currents tend to be only possible when you have free theories, but let's suppose we have T mu1 up to μl, and we want to consider the 3-point functions of our set of and investigate how many possibilities there are just by solving the relevant algebraic equations. I mean, it's a slightly non-trivial task to do, but it's in principle straightforward. In d equal to 3, I mean, quite recently, or relatively recently, Maldaceno and Zabodiev showed that there are only 2 possibilities, which correspond to free scalars plus fermions. Actually, there is another possibility if you allow an epsilon tensor. And this, so normally when you write down these formally, you tend to assume that there's going to be no epsilon tensors in this because they're associated with odd parity. However, if you go to d equal to 4, then the number of possibilities is the minimum of Li plus 1. So the number of possibilities you get, so this corresponds in this particular case, the spin here is 2 in each case, so the minimum there is 2, and you add 1 gives you the 3 possibilities which I've just described. And these are, in some sense, related to the possible higher spin theories that you can construct involving higher multiform gauge fields. So that's an interesting area of research which has been developed in the last 2 or 3 years about showing how one has, if one has high spin conserved currents, you must have free theories. Well, that's not to be unexpected, but then you can also look at the situation where the higher spin conservation equations are only broken by a little bit, and then try to do some kind of perturbation in that context. But that's going further than what I wanted to describe.
You mean up to tensors, and then you can always take a bunch of such.
You mean by, well,
you can always take many scalars and themselves.
yeah, you mean by just effectively multiplying 2 such things together?
Yeah, I mean, like if you take any 4 sypersymmetric and just accompany to 0, it's also.
Yeah, I thought that myself that there was a trivial solution in that kind of way. I'm not wholly convinced that it will satisfy. I mean, if there's a trivial solution, then these things will factorize into products of things with lower dimension. But you have to symmetrize over all the indices for all the coordinates to which it's not just a simple product, because the indices themselves, you're interested in tensors which have completely symmetrized indices.
But didn't I then just find the complex sample? I mean, take any 4 and set the values back to 0.
Well, I mean, of course, yeah, I mean, you're I think in effect they're assuming within these class of theories that they're discussing that there is a unique energy momentum tensor. In the sense, even in Yang-Mills theory of n equals 4 instance, it's the sum of the vector bit, the fermion bit, and the scalar bit, which in the free theory describe completely separate things, but I think that particular theory breaks up into a product of scalars, fermions, and vectors in that particular limit, each of which has its own energy momentum tensor. So I think there's a further assumption that within this framework that there is a unique energy momentum tensor, which would preclude that possibility. Well, I agree that no-go theorems are always a challenge to find a loophole, but it's the general folk wisdom is that if you have spins higher than 2, which are conserved, then the only possibilities are free theories, and this is in effect one way of trying to prove that possibility. Well, anyway, it's not a route I want to go down, but the one thing that you can immediately do if you understand the three-point function is to talk about the operator product expansion. So the conformal field theories are associated with sets of fields which are described by their scaling dimensions and also by their spins, but now we want to provide, if you like, some way of multiplying them together, and this is the operator product expansion. So the idea then is that if we take two fields, by the way, I'm assuming here that these fields are conformal primary. The descendants of conformal primary are basically the fields you get just by acting on it with various derivatives. So the idea here is that for any product of two fields, here for simplicity I'm writing it down as if there are scalars, but you can generalize it to the case of spins, can be, so here I'm going to write equals, and it really is equals in a way which I shall describe, over some set of operators which I'll denote by O, x12 squared, well, it depends on the dimensions of these operators. There's going to be some coefficient here which is some number, so I have to assume that I've chosen some normalization for the fields phi1, phi2, and also the operator O in due course. Normally you do that by imposing the requirement that the two-point function has coefficient 1. So that determines the normalization. And then this is summed over some bunch of fields where here I is a spin index, and then we have to introduce some function here of this kind, where this is a object which is determined. So this is, so we don't know this object necessarily, but this is something which has properties which I'll describe in just a moment. The property is that this reproduces the three-point function. So the idea here is that if we consider phi1 of x1, phi2 of x2, and let's write oi of x3, and if we substitute this formula in, then you'll only pick out a particular contribution corresponding to that operator, and we must have that C, well in the simplest case, is a differential operator defined by the property it does this, namely x12 squared, a half delta 1 plus delta 2. X2, well, that should be x13, x2 a half delta 2. So hopefully you can see that just by this particular formula here, so I've effectively pulled out this particular factor, and this derivative thing is meant to satisfy that it converts this thing, which is what would appear in O of x2, O of x3, and it splits it into this product of two contributions in such a way as to reproduce the three-point function which you have over here. Now you can construct differential operators which do that. They're slightly complicated objects, but they're in principle perfectly straightforward objects. And what you're doing here is that if you think of this, is that this provides you a sum. So this can be expanded as a sum over things which involve d2 to the n. So So the term for n equal to 0 here is the primary operator, and these various derivatives, you're summing up the contributions not only of the operator, but what are called all its descendants. And then this particular expansion, once you apply it in a three-point function, gives you something which is convergent in a finite region. Namely, you have to make basically x12 is smaller than any of the other separations in the particular problem that you're dealing with, but so long as that's the case, then this should be a convergent expansion as you sum over operators here. Now normally in quantum field theory nothing is convergent, everything is asymptotic, but in this particular kind of framework we're dealing with honest to goodness convergent expansions. I mean, there can be singularities, just like in any analytic function. When you expand it, when you start expanding it when the value of the variable you're expanding in has a magnitude larger than the distance to the nearest singularity, then the expansion will not converge, and that's more or less what happens in this particular case. Now, if you know the operator product expansion for any pairs of operators in your theory, as well as knowing all their spins and scale dimensions, in principle you can determine all correlation functions. Because, for instance, supposing we had two operators and then some other contributions which I haven't specified, then I can always express this using the operator product expansion. So this involves, in terms of contributions of this form. So you can reduce any endpoint function involving n fields to one with n minus 1, so long as you know what these coefficients are. So that you need to know these numbers. Everything else in that expression is effectively determined. This is a sort of, in principle, a known object which you can construct. You know what operators should appear if you know what the spectrum of operators in the theory is. And then you can, so you need to know these numbers here. Of course, in the case with spin, as I've said, there may be more than one operator, more than one possibility here, but there's only a finite number of possibilities which can occur. So basically the data for conformal field theory are basically you need to know the set of all deltas and spins in that particular theory, and you have to know the OPE coefficients. And at least if you know all that, then in principle you've determined all possible correlation functions in that particular theory. Let me just make a brief remark about, in some cases, the coefficients are determined. Suppose we take the energy momentum tensor. In this case, there are what are called Born identities, which relate this to phi 2 of x2. The point is that the energy momentum tensor is special properties that, because it's related to the generators of conformal transformations and so on, which effectively, not necessarily completely, but at least partially determine this three-point function in terms of a lower point function. So actually, if we go back to this case over here, where we have three energy momentum tensors, then there are three numbers in principle which characterize that. But one of these numbers is related to the two-point function. So there's just a unique number which is associated with this, and so there are three numbers here one of which you can relate to the value of this quantity. I should say that normally, as I've said already, you can choose the normalization of the two-point function to be 1. In this case, it's not natural to choose it to 1 because you can determine the normalization of the energy momentum tensor in order to get a nice form for the Ward identities, in which case this has a definite coefficient Ct. And this is a number which, in principle, you would want to determine in any conformal field theory. And in 2 dimensions, this becomes little c, the Virasoro central charge. And this is one possible generalization of the Virasoro central charge to higher dimensions, which has the property that it determines the normalization of the energy momentum tensor. However, this also contains, so in 4 dimensions, the anomaly that determines C in 2 dimensions has 2 numbers, A and C, and in many ways A is a more obvious generalization of the Virasoro central charge to 4 dimensions than the quantity Ct itself. Okay, so let's now go on to discuss a situation where we have 4 operators rather than just 3, and then we can find some novel things which constrain the possibilities for a conformal field theory. So come back to the left-hand side. So I said that the thing which involved 3 fields is more or less uniquely determined, whereas the case of 4 is rather different. So let's consider line 1. Again, for simplicity, I consider the case where there are only scalar fields. So I gave rise to an argument previously to suggest that there was essentially a unique possibility in 3 points. Now in this case, suppose we have 4 points, so in d dimensions, so we have 4 times d independent numbers, but the conformal group acting on it will subtract off. So, but of course, 4 points define a plane, so these points define a plane, and you can rotate the plane around in whatever space you're dealing with, and so we have to, so we add back in. So this is OD minus 2, at least the dimension of it. And that, if you work it out, is equal to 2. So what this means is that there are 2 invariants that you can construct under conformal transformations when you've got 4 points. In fact, it's easy to write them down because we just have to write, well, standard names for them are U, so you can see the point is that there's 1, 2 in the top and another 2 in the bottom, similarly 1, 4. So when you do a conformal transformation and these separations scale by factors at 1 and at 2, these factors cancel between the numerator and the denominator. And then there's another one you can write down. V is equal to x14 squared. So these are the 2 conformal invariants that you can have for 4 points. But now let's consider, well, let's simplicity consider all the phi I to be the same. So there's going to be one factor, let's say x12 squared, x34 squared, delta phi. and then you can multiply it by some function of the two invariants. So if we have a 4-point function involving 4 points, then we have in principle arbitrary function of the two invariants here, u and v. And so this is the quantity which one would like to determine in principle if you want to fully describe what this object is. Now, that's one of the things I wanted to describe in the rest of this afternoon's talk. I mean, first of all, one has to note that there are certain symmetries associated with this, assuming that we now go to the situation where all the fields are the same. If we, let's say, interchange x1 and x2, then it's clear, I hope, that u will go to u over v, and v goes to 1 over v. And if we consider this function here, this will say that this is going to be equal to so that's one transformation that you can take into account. Now let's suppose that we interchange 1 and 3. So if you interchange 1 and 3, so this is going to be x2, 3, this is going to be x1, 4, and the denominator remains unchanged. So basically u and v interchange with each other. But we've already spoilt this symmetry by bringing this factor out the front. When we interchange x1 and x2, this factor remains unchanged, but in this particular case, we would have to impose the requirement that f of u and v is equal to u over v. So delta phi f of v. So this function that we're writing down would have to be a function, at least if all these fields are the same, satisfying those particular relationships. Now let's imagine that we want to look at the operator product expansion that I've described. Suppose we take the operator product of these two fields. So we want to write that phi1, and I'll be schematic here, is equal to sum over operators O, C, some. So this is a schematic thing where we're expanding over operators which have, let's say, scale dimension delta and spin L. So that this here you can describe by a tensor. Yeah?
What is this function? Should equal if you are different from
I mean, I'm assuming that all the things are the same. It's just these things are only the case. In general, you would have to define a matrix, let's say. In general, there would be an object F1, 2, 3, 4 UV, which would be equal to F2, 1, 3, 4 U over V, 1 over V. That kind of thing. But so if you allowed for all possibilities, there would be something of that kind. But just for simplicity, let's consider the case where there's just the same fields. The basic ideas will extend to this case, but with a bit more complication. So now we're imagining we're inserting this into this 4-point function. Now what we're going to get is that once we've pulled out all these extraneous factors, we're going to get an expansion of the form FUV is equal to sum over, well, let's imagine that there's some coefficient in here. Well, actually, I'm assuming these are the same now, aren't I? So let's assume that this coefficient is C, denoted by the operator O. So it's going to be a sum over contributions for all the different operators of CO squared of G delta, some function of U and V, which depends on the scale dimension delta and also the angular momentum L. So these are, in principle, known functions. And if anybody's done any work on scattering, it's like a partial wave expansion when we have a scattering amplitude depending both on energy and the angle of scattering. You can decompose this into contributions for each L, and we have an expansion. So typically speaking, you would have F of E and theta to be sum over L of AL of E times PL of cos theta. So that's typically what you would have for a partial wave expansion, and this is a generalization of that to this situation. But these are now numbers which are positive, and this will play an important role because in just a moment. Now, what are these functions? Well, they're characterized in various ways, namely that they're things as U goes to 0 and V goes to 1 has the property they behave like the half delta minus L and then 1 minus V. So the fact that we're dealing with operators of certain spin is expressed in the fact that they have this particular dependence on 1 minus V and delta. So this is the limiting situation as U goes to 0 and V goes to 1, but there are obviously much more complicated objects than that in general. Now, one special case that it's useful to separate is that we can always consider the identity operator. The identity operator tends to be present, well, if the first contribution is going to be 1 over x12 squared to the delta phi, and then plus dot dot dot. So this operator, so the identity is always an operator which is present in any conformal field theory, and in this case we have G00 is equal to 1, and more or less by choice of normalization that C1 squared is equal to 1. So we always can separate off that particular contribution. So that means, no, it's slightly simpler to write this expansion now. I'll separate off the contribution of the identity and leave the rest. So that's a matter of choice, and now of course these other contributions are ones which are less important as U goes to 0. So the point is that as delta increases, this thing vanishes more rapidly as U goes to 0. The case for which the delta minus L is a minimum is when you have the identity operator and it's equal to 0. Now, let's consider the following combination, and let's assume we now remember, I want to try and consider a situation where we have the symmetry, so I'm going to consider this particular equation. So the first equation you can satisfy, so the symmetry under 1 interchange 2 basically implies that L is even. So that's the only restriction that you get from the first equation. But now let's consider what the second equation gives, and let's consider the following combination. So I've chosen that combination because the basic, so I'm going to consider the expansion in terms of these conformal, or sometimes these are conformal partial waves, or sometimes referred to as conformal blocks. So I'm considering this expansion both for the f, so I'm applying the expansion both for f of u and v, and also f of v and u. So that will give rise to the following equation, namely that 1 is equal to sum over O, all possible operators, of A of O squared times F of delta and L and U and V. So this equation needs to be valid for any possible U and V. And it needs to be valid for these coefficients here to be positive. And this is basically an equation which has non-trivial consequences, even though it may look rather innocuous. Basically, you can call this the bootstrap equation. This constrains the spectra of deltas and L's. So we're summing over here possible deltas and L's in the theory that we hope is going to be a proper conformal field theory. And the idea is that you try to consider this in a region where it converges, obviously. So it converges. Basically, the original expansion here should converge for u sufficiently small, and the other expansion when v and u are interchanged should converge when v is sufficiently small, and you look at the point where u and v is equal to a quarter. And so both the expansion in terms of the original product of 5x1 and 5x2 should be convergent, and then also the expansion where you consider the operator product of 5x1 and 5x3 should be convergent as well. And the point is that if you choose an arbitrary spectrum for delta and L, and then let's suppose you can find some region of u and v near this point in such a way that all these contributions are negative, you could never satisfy that equation. Well, normally what happens is that people do a Taylor expansion, both in u and v, about this point, and then try to find some kind of linear combination of the coefficients in such a way that it would be negative for suitable values of delta and L. So let me just describe a little bit more how this works. Let's consider the case of a free theory. So in the case of a free theory, if we consider the 4-point function, then the contributions you can get, there's no interactions, so that we can basically have the 4-point function product of 2-point functions. And so that we can have the other graphs that you can have are this and this. And if you work this out, in this case delta phi is equal to d minus 2. And the actual formula for the this quantity is equal to 1. So this is the contribution involved in the identity operator, and then there's a contribution u to the d minus 2 plus v to the d minus, sorry, u over v to the d minus 2. So that's special to a free theory. But the point about a free theory is that when you consider the operator product of phi of x1 and phi of x2, say, the only operators are going to be ones which have delta is equal to L plus d minus 2. So that's rather special to a free theory. It's rather unique, namely that they're all the fields that you can get just by taking various derivatives of that form. And so there's going to be an expansion in this case. So this particular is going to be a sum over, well, you can sum over L of G of L plus d minus 2 and L. And there's some coefficients here, which you can, well, let's write them as a function of L only. And you can work out what they are, and in fact you can give a formula which is just a basic product of gamma functions, but let me just quote the value. So for large L, they're roughly of this form. So in principle there's some dependence on the dimension in there, but you can see that this whole expansion converges rather rapidly, but there are lots of states that you might think would be present which have zero contribution. Namely, the only states which are present are here, but you can have, so this is what's called leading twist. So the twist is always delta minus L, and remember that I tried to show that delta minus L has a lower bound for any conformal theory, field theory which is unitary. In fact, this is the lowest bound that you can have. But in principle, you can have larger values of this. So there are lots of operators which could be present which have zero contribution. Now, if you vary things a little bit, supposing we try to consider a theory in which delta phi was a little bit bigger than this, and then see what restrictions you can have. So what you can show is that if you consider the first, so phi, supposing this has scale dimension delta phi, then the first operator that you would expect is phi squared. So phi squared is just when you take the contribution, in the free theory it's just when you take the normal product, normal-ordered product of two ordinary scalar fields. So phi in the free theory has dimension 1/2 d minus 2, and phi squared in the free theory has dimension d minus 2. Now let's imagine that we consider a theory, we try to solve these bootstrap type equations for some arbitrary initial delta phi, a little bit bigger than this. What freedom do we have for the choice of the lowest, so this is the lowest dimension scalar operator that you can have. And what people have shown, this was shown by 4 authors, Rattazzi, Richkoff, Bonnet and Vichy about 4 or 5 years ago now, is that we must have delta phi squared is less than of order of some numerical coefficient times delta phi. Well, they did this in 4 dimensions, so this is for d equal to 4. So the point is that this gives you a non-trivial bound. It means you can't make this dimension higher than, I should have put, this is going to be plus 2. The point is that when delta phi is equal to 1, we have a free theory, and in that case delta phi squared is equal to 2. And as you perturb it away from this isn't a perturbation, it's if you make an assumption that we're dealing with a scalar operator whose dimension is a little bit bigger than 1, you're constrained to have scalar operators which are bounded by this amount. Now this is something which depends on numerical work, really. I mean, basically this becomes a problem in linear programming because the idea is that you expand these quantities, this quantity curly f, around the crossing symmetry point, and so this is all done numerically. There's relatively little analytic understanding of why this all works, at least at the present time. Now, more recently, this has been extended to many other theories, but let me just describe in some detail, well, not in some detail, but an outline, what results can be obtained for the Ising model. So the Ising model, and in particular in d equal to 3, which as far as we know is not an integrable theory. By the way, I should say that there is not any immediate connection between a theory being conformal and a theory being integrable. There are many theories which are massive and integrable, and there are also conformal theories which are not integrable, and the Ising model in 3 dimensions is one of these. So it's not, at least as far as we know. Yeah, okay, well I'll finish in perhaps a bit less than. But anyway, so the Ising model itself is in 3 dimensions clearly of something of experimental interest, and clearly also of huge theoretical interest. And many people since the time of Wilson in the 1970s have been calculating what are called the critical exponents. The critical exponents of the Ising model are just related to the scaling dimensions of various operators. So the critical exponents are equal to the deltas of the various operators. I should say that we're interested in the Ising model near a critical point. So the correlation length has diverged to infinity, and so the fine structure of the Ising model is unimportant. The fact that we're dealing with a particular cubic lattice or some other lattice is irrelevant. That we're dealing with a theory which can be described by a conformal field theory. And the conformal field theory which contains certain operators, and it's those operators whose scale dimension we want to try and determine as best we can. Now, what are the operators in this theory? Well, this theory is in some sense related to a scalar field theory, but where we have certain spin operators, sigma, we have an operator epsilon, which in some sense is sigma squared. And then we also have the energy momentum tensor. So this is a very minimal theory in that the spectrum of operators is much more... And of course there are infinitely many operators, but these are the lowest dimension. So this is the lowest dimension. Now what I should emphasize is that when the idea here is that you consider the 4-point function of the energy momentum tensor. Sorry, not of the spin operator. So sigma, 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 sigma. And you play the games that I've described. Now I should say that whilst we know these objects pretty well in 4 dimensions, it's much less clear-cut what these things are in 3 dimensions. There's no explicit formulae for these objects in 3 dimensions, but we can find them numerically to quite a high degree of accuracy. So in that sense it's a solved problem, but analytically there is no simple solution in terms of functions you can look up in a textbook. In 4 dimensions you can write these basically in terms of hypergeometric functions, but so that's in principle a straightforward thing to work out. So, as I've tried to describe, when you apply these numerical methods to this kind of bootstrap thing, you only get bounds. So the point is, you can restrict the possible values of delta and L, but you can't determine them from that equation. I mean, that's far too much to hope for. But what you can show is that if you look, there are sort of kinks in the bands. So these kinks are almost certainly related to the fact that some operators that you think are present are becoming null. I mean, the 2-dimensional Ising model you essentially solve by saying that one of the states which might appear is absent. You impose a condition that this state is 0, and then effectively this gives you differential equations which determine the whole 4-point function in that particular theory. So if you analyse the theory, and it depends as you vary epsilon. So if you increase the epsilon, the whole thing fails, which is just similar to what I've described already. And I should say that there is another state, epsilon prime. And if you start making this epsilon prime have a dimension which is too big, then this also removes all the possibilities of finding a solution. Anyway, if you play these games, you will find values. Well, I've just taken them from the paper which appeared this year and slightly truncated them. So these are numerical obtained, in which all those figures are significant. And then, for instance, we find, so this is the value then delta epsilon, the first state, is equal to 1.4127. And then delta epsilon prime is equal to 3.83. Anyway, with some degree of heuristic numerical analysis, you can find well-defined predictive numbers for the scale dimensions of the various operators. This for the lowest spin one, this for the first scalar state, this for the next one. There's also an engine momentum tensor which has dimensions. So in this particular theory, delta t is going to be equal to 3, because of course the dimension of this is always going to be equal to d. So this is the where we are as far as I know. We can try to extend this to more complicated theories. This has been done to some extent. This is all depends on numerical analysis. You're not going to be able to solve the Ising model in this way, except insofar that you determine these scale dimensions very accurately, subject to certain assumptions. And by the way, these values are competitive with all the historical work that people have done over 30 or 40 years in trying to work out the scaling dimensions for this particular theory, the Ising model. But of course there are many generalizations of the Ising model which are relevant in condensed matter physics in 3 dimensions. One can extend this to 4 dimensions and then also in principle to higher dimensions. I mean, one interesting challenge which I offer up is to prove there are no non-trivial CFTs in D greater than 6. I'll talk a bit more about some other cases, but nevertheless, it's sort of widely supposed to be the case that there are no conformal field theories in higher than 6 dimensions, which are non-trivial. There are free theories for sure, but not conformal field theories. And whether we could ever show that, you might be able to do that by this kind of analysis. But I think I'll probably stop there for today, because the last lecture tomorrow I'll talk about generalizations to include supersymmetry. Questions?